This video I am going to explain 0R1 knapsack problem by using solving 0R1 knapsack problem by using branch and bound. So first I will give little introduction about branch and bound. After that I will tell you which method is very easy for solving 0R1 knapsack problem under branch and bound. So what is branch and bound? That name itself, branching, means constructing tree structure based on the constraints. Constraints are bounding function. Okay, na? So based on those constraints, so we are going to expand the tree structure. Okay, so we can solve the problem, any problem which can be solvable under branch and bound in two different ways. One is first in first out branch and bound, another one is LC branch and bound. So the problem in first in first out branch and bound is once you start at root node, you must expand root node completely. So that means we need to select a root node as E node, means expanding node. We need to expand completely, means we need to visit all the children of the respective node. So here we use Q as data structure in first out. So store all the children in queue and select first node for the next exploration. So like that, we need to expand all the nodes from top to bottom, left to right. Okay, but in LC branch and bound, the important concept in LC branch and bound is we are supposed to select one node as expanding node. We need to start at root node, expand root node completely. So once after reaching children, we need to calculate the cost value of each and every child, cost value of each and every child based on constraint. So after calculating cost value of each and every child of the respective node, we need to select the minimum cost node as next E node. We need not expand all the children of the respective node. Once you expand, we must select the least cost node for next exploration. So that is the least cost branch and bound. But at every level, we are going to expand only one node. That node has minimum cost than all the remaining nodes. Okay, so now I will tell you little information about branch and bound now. What is branch and bound? Sorry, LC branch and bound. So LC branch and bound means least cost branch and bound. So according to branch and bound, you are supposed to draw this straight space tree. Okay, na? Means tree structure. And according to bounding function or constraints, you are supposed to calculate a cost value as well as upper bound. Cost value we need to calculate, upper bound we need to calculate. Okay, now. So after calculating cost values of all the children, you must compare cost values. Okay, now. So here, before selecting any node, first we need to kill or omit some nodes here. So those nodes cost value is greater than upper. Okay, now every time we need to calculate upper bound value. Okay, now that upper bound value is less than the any node cost value. Immediately kill that particular node. Okay, now otherwise we need to select minimum cost node for a node as next E node. We need to expand that particular node. Okay, now repeat these steps. Okay, calculating cost value and upper bound. If any node cost value is greater than upper bound, we are supposed to kill that particular node. Otherwise, or after killing, whatever the remaining nodes that are there, we need to select minimum cost node and select it as E node and expand it. So repeat this particular process, and finally, a minimum cost node will be selected as answer node at leaf level. Okay, now from that particular node, we go backward direction up to root node. So that particular direction is producing path of the respective solution, and whatever the edges that are associated, those edges are the solutions. Okay, so this is about LC branch and bound. Now I will show you how we can solve 0R1 knapsack problem using LC branch and bound. Okay, suppose if we take this instance, there are 4 objects, and 4 objects profits are 10, 10, 12, 18, and weights are 2, 4, 6, 9. Okay, your constraint is you are supposed to select all the elements, okay, na, and place them in the knapsack. So in such a way that you must get the maximum profit, and that too the knapsack capacity should not exceed. So whatever the elements you include in knapsack, those elements weight sum should be less than or equal to 15. So this is the constraint. So you will need to start from root node. You must calculate the root node upper bound and root node cost value. So upper bound is nothing but the cost, the total sum of the profits. That too, we need to select all the elements in sequence from first element. Okay, now, but here we need to construct here we are going to construct the solution in fixed tuple sized format. Fixed tuple sized means we need to represent each and every element solution as either yes or no. I will show you in tree structure format, don't worry. Okay, so now start with the first element. Here we are going to calculate root node upper bound and root node cost value. Okay, na? Now start with the first element. Whatever the elements we can select in the sequence from first element to the possible element number. Suppose, what is the first element weight? 2. Okay, second element weight is 4. Third element weight is 6. So 2 plus 4, 6 plus 6, 12. Still, this 12 is less than 15. Suppose, if you try to include fourth element also, fourth element weight is 9. 12 plus 9, 21. So it exceeds. It exceeds the knapsack capacity. So in this sequence, we can select first 3 elements. Then what about the total profit we get? That becomes upper bound. So 10 plus 10 plus 12 is 32, but we are representing that particular upper bound with the negative sign. So summation of minus summation of pi is minus 32. Okay, na? So this minus 32 is the upper bound of root node. Okay. Now involve this upper bound in Caustic calculation. Very simple. Caustic calculation equation is upper bound of the respective node minus the total knapsack capacity minus whatever the elements you select, those elements total weight by selected elements weight. This is selected elements weight by actual remaining elements, because remaining element is fourth element. Actual remaining elements in weight into actual remaining elements profit. What we are doing here, just we are subtracting this entire term from upper bound. So upper bound is calculated by summation of all the selected elements weight profits. So here we are involving upper bound in Caustic calculation. That is upper bound of the respective node minus m is the total capacity of knapsack minus all the selected elements total weight by actual weights remaining into actual profit of the remaining objects. Okay, actual profit of the remaining objects. See here, now we selected first 3 elements. So total profit is 32. So that becomes weight minus 32. 15 is the total weight of the capacity of knapsack minus current total weight of selected elements. Selected elements weight is first 3 elements weight 12 by actual remaining weight. This is not omitted, this is remained. In the sequence, this is remained. So remaining element weight is 9 into remaining element profit. Remaining element profit is 18. So minus 32 minus, so this is 3 by 9 into 2, 6. This becomes 6. So minus 38. See here. So first node, cost value is minus 38, upper bound is minus 32. So here we are using tag. Tag is representing whether you selected that element or not. Initially we have not yet selected any element. That's why take any big negative number. So that becomes tag. Okay. Now the root node cost value is minus 38. Root node upper bound is minus 32. Then now we are going to select first element. So here first element has 2 choices. One is first element is selected, another one is first element is rejected. Now we will calculate a cost value and upper bound of these 2 cases. Now first select node 2. Okay, na? Node 2 means we consider element. Okay, na? So considered element weight is 2. Now once after considering element, whatever the remaining elements we select in the sequence from that element, only as previous one, only first 3 elements we can select. Then profit is first 3 elements profit minus first 3 elements profit, that is minus 32. Then what about cost? Same. Here this element is remained. So remaining element weight into remaining element profit. Just involve these items in the equation. Okay, na? So minus 38. Same as first node we get. So minus 38, minus 32. But tag is different. Tag means here we selected first element. So tag is representing that whether you selected element or not. Okay, na? So that is node 2 information. What about node 3 information? What is node 3? First element is rejected. Now just completely omit this particular element from the consideration of calculating node 3 cost and node 3 upper bound. So what is node 3 upper bound now? Okay, na? So node 3 upper bound is, node 3 is x1 equal to 0. So x1 means first element is rejected. Then from the second element, how many elements we can select in sequence we find out. So for second we can select, because 4 capacity is 15. Third element we can select 6 plus 4 10, the capacity is 15. But can we select fourth element, because 6 plus 4 10, if we include fourth element it becomes 19, but capacity is only 15. So we cannot select it. So this becomes a remaining element. This is omitted completely. Only we can select second element and third element. What about second element and third element profit? 10 and 12. So minus of summation pi, so minus 22. So this is upper bound is minus 22. Just involve minus 22 in this calculation. So minus 22 minus of knapsack capacity minus selected elements weight. Selected elements weight is 6 plus 4 10. by remaining element 9 into remaining element profit 18. So minus 22 minus 5 by 9 into 18 means 10. So minus 32. So this is minus 32. So what is the constraint now? So before selecting any node as E node, we must compare cost values of these two nodes. Node 2 cost value is minus 38. Node 3 cost value is minus 32. Which is lesser? Node 2 cost value is less. Then we select node 2 as next expanding node. Okay. So node 2 as next expanding node. So now expand node 2 as 4 and 5. Because no, at node 2 we have choice of selecting second element. We selected first element now. Choice of selecting second element. So here second element has two choices. One is with x2, another one is without x2. With x2 means x2 equal to 1. Without x2 means x2 equal to 0. So first calculate node number 4 related cost and upper bound. How we reached node number 4? By considering element 1 and element 2. So by considering element 1 and element 2, we reached 4. Then in this sequence, next how many elements we can select, including node 1 and node 2, element 1 and element 2. Okay na? So element 1 weight is 2, element 2 weight is 4. So 4 plus 2, 6. Then include element 3. Element 3 weight is 6. So 12. Can we include element 4? No, we cannot include element 4. Element 4 cost is, weight is 9. So first 3 elements we can include. So first 3 elements total profit is minus 32. Okay na? So minus 32. So add minus 32 as upper bound. Then involve minus 32 in cost calculation. The remaining element is 4. Fourth element we cannot select because first 2 elements are selected. In this sequence we can select third element, but we cannot select fourth element in this sequence. Then the same as the previous node we get the values. Okay na? So there is no change because the element selection in first node, second node and third node are same. And remaining element is fourth element in these 3 nodes. Then what about node number 5? Node number 5 is x2 is 0. So x1 is selected, x2 is rejected. Then how many elements we can select in the sequence we will check. So x1 is selected, weight is 2 units. x2 rejected, completely omit this particular node for calculating cost values of node 5. Completely omit this node element. Then we can select second element. So 6 plus 2, 8. Can we select fourth element? No. 8 plus 9, 17 it gets. So that's why we can select only first element and third element. Then what about upper bound? First element and third element is 10 plus 12, 22, minus 22. Okay now. Then what about the cost value now? So minus 22 minus of same. Here also fourth node is remaining node. Fourth element is remaining element now. So remaining, but what is numerator? Numerator is capacity of knapsack minus selected elements weight. What is selected elements weight? First element is selected, third element is selected. So weight 8 by remaining element is 9 into remaining element capacity profit is 8. So 7 by 9 into 18, 14, minus 22, minus 14, minus 36. So cost value is minus 36. Here cost value is minus 38. Okay na? Suppose if cost values are same, then we compare upper bound values. If cost value is here is 38, here also 38, then compare upper bound values. Whichever node upper bound value is smaller, then we select that node as next E node. But here this cost value is smaller. Node 4 cost value is smaller. Then select node 4 as next E node. Node 4 as next E node. Okay. So this node 4 is now selected as next E node. Then the choice is for third element. Now again apply 2 choices. So select third element or reject third element. First calculate node 6 value because node 4, node 5 are already named. Then node 4 is expanded as 6 and 7. Okay, give the node numbers in sequence. 6 and 7. Now calculate node 6 upper bound. Okay, now how can we calculate node 6 upper bound? How we reached 6? By selecting node element 1, element 2 and element 3. So first 3 elements are selected. Can we select fourth element? No. First 3 elements summation is 12. Then if we include the next element, then if we include next element, then it becomes 21. Then we cannot select next element. You are supposed to write those weights also here. Okay, now I forgot writing here, but anyway, previous slide is containing weights and profits. Okay, now then same thing we get as a fourth node, we get the same as fifth and sixth node also because in sequence we select the first 3 elements, we cannot select fourth element. So fourth element is treated as remaining element now. So 15 minus 12 by 9 into 18. So 3 by 9 into 18 minus 38. Again we get minus 38 as cost value. Upper bound is first 3 elements profit minus first 3 elements profit minus 32. But what about node number 7 now? Now how we reached node number 7? By considering element 1 and rejecting element 3. Element 1 and element 2 are selected, element 3 is rejected. Okay, na? Can we select element 4? Yes. 4 plus 2, 6. 6 plus 9, 15. Yeah. Knapsack capacity is also 15. Then we can select first two elements and fourth element, because third element is rejected. Third element is rejected. We completely omit this particular element for calculating node 7 value. So first three elements are selected. First two elements and fourth element is selected. No, there is no remaining element. Okay, na? So first two elements and fourth element is selected. So minus 38, 15 minus three elements, first two elements and last element. First two elements sum is 6 plus last element weight is 9, 15. So 15 minus 15 by, there is no remaining element. So remaining element weight is 0. Profit is also 0. So minus 38 we get. Here also minus 38 we got. Here also minus 38 you got. Okay, na? Now, here cost values are same. Then what I told earlier, if cost values of both the nodes are same, then compare upper bound values. So whichever node upper bound value is smaller, then expand that node. See, node 7 upper bound is smaller, minus 38. Here minus 32. So minus 32 is greater than minus 38. Then select 7 for next exploration. So the 7 is the next E node now. Now expand 7 as 8 and 9. So here we need to represent a choice for fourth element. The x4 equal to 1, x4 equal to 0. Suppose if you select x4 equal to 1, then what about node 8 cast and upper bound? If you select if you reject the fourth element, then what about node number 9? See here, how we reach it in 9 and 8 we will see. So first element is selected, second element is selected, third element is rejected, fourth element is selected. Okay, na? Then only we got a row that means node number 8. Then it is similar to this one, because first two elements are selected, third element is rejected, then fourth element we select. Then node number 7, same result we get. Node number 7 result we get. Okay, na? Then node number 8 is first two elements and last element. First two elements and last element. So minus 38. Profit is minus 38. So minus 38 minus first two elements and last element weight value is 15. There is no remaining item because third item is rejected, fourth item is selected, first two elements and fourth element is selected. There is no remaining element, so this is become 0. This is also 0. Then this total term vanishes. So minus 38. Then what about upper bound of 9? How we reached 9? First two elements are selected, next two elements are rejected. So first two elements are selected, first two elements are selected, next two elements are rejected. So profit is 20. Okay, na? Profit is 20. So total profit is 20, that becomes upper bound. Total profit is 20, that becomes upper bound. Okay, na? So what about cost value? Minus 20 minus of selected element weight values are 6. So 15 minus 6 by, there is no remaining element because next two elements are rejected. We need not consider those two elements. So next two elements are rejected. So profit and weight values are 0. So minus 20. Okay, na? So we reach the last level now. So 8th node cost value and profit values are these two, and 9th node cost value and profit weight values are these two. So upper bound is minus 38. Here upper bound is minus 20. A cost value of node 8 is minus 38. A cost value of node 9 is minus 20. So, okay. So node 4 is element 4 is selected here. Element 4 is rejected here. Then immediately compare at least leaf level. Now we reach a leaf level now. At leaf level also compare node two nodes of cost values. So 8th node cost value is smaller than 9th node cost value. So this is minus 38. This is minus 20. Okay. So minus 38 smaller. Now at leaf level, after selecting last node with the minimum cost, then that node becomes answer node now. So node 8 is answer node now. What is answer path? Just simply trace back from answer node to root node. So 8, 7, 4, 2, 1 is answer path. Or we can write it as 1, 2, 4, 7, 8 as answer path. What about answer now? X1 equal to 1, X2 equal to 1, X3 equal to 0, X4 equal to 1 is answer. So this is answer. Answer node is 8. Answer path is 1, 2, 4, 7, 8. And solution is X1 equal to 1, X2 equal to 1, X3 equal to 0, X4 equal to 1. So these values. Now verify how much profit and how much weight is included into knapsack. How much profit we get? P1 into X1 plus P2 into X2 plus P3 into X3 plus P4 into X4. P1 10 into X1 1 plus 10 into 1. And next 12 into 0 and 18 into 1. So 38 you got. Then what about total weight included into knapsack? With W1 into X1, W2 into X2, W3 into X3, W4 into X4. So 2 into 1 plus 4 into 1 plus 6 into 0 plus 9 into 1. 15. Then knapsack is completely filled. And from that we got 38 as total profit. If we observe the problem, how we expanded the tree structure. Branch and bound means expanding tree structure, expanding or constructing state space tree based on LC or first in first out branch and bound. We need to expand the tree structure. In first in first out branch and bound, we need to expand all the nodes from left to right, top to bottom until reaching the answer node. But in LC branch and bound, at each and every level, we are supposed to select only one node which has less cost than all the remaining nodes, and selected node must be expanded completely. Okay, na? Like this. So start from root node, calculate root node cost, upper bound, and here the cost and upper bound value is calculated by considering all the elements in sequence. If any element is rejected, then start from first node and the rejected node will be omitted. In the sequence, how many nodes we can select, we need to find. So that too, the selected weight values must be less than or equal to knapsack capacity. So according to that, we need to select all the elements in the sequence. So at each and every node, we need to calculate upper bound and cost value. Once you calculate cost value, compare those two cost values, and the smaller cost value node should become E node and expand it. And again apply the same procedure with respect to element and without respect to element. We need to expand the nodes, and the node cost values again we need to calculate. Upper bounds we need to calculate, again compare cost values of those two nodes. If cost values are same, then compare upper bounds, and upper bound value is less, then we need to expand that particular node. If cost value is less, then we need to expand that particular node. So like this, we need to expand up to leaf level. So once after reaching leaf level like this, again we need to compare the cost values of those two nodes. If cost value is less, then we need to select that particular node as answer node. If both the nodes cost values are same, then compare upper bounds. And if upper bound is smaller, if upper bound of one particular node is smaller than upper bound of another node, then treat it as answer node and trace back from that particular answer node to root node, and draw the path. And on that particular edges, we assign the solutions. Then simply write those solutions as optimal solutions. Then verify whether we get the 38 or not, because at root node we got 38 as a value, cost value. The 38 is the profit. Whether we get that particular profit or not, we need to check by applying the solutions with the profits, and whether completely knapsack completely filled by with the selected elements or not, we need to cross check. Okay, na? So after cross checking, we got 15 is the total weight included into knapsack, and 38 is the profit we got from this particular problem. Okay, so in this way, whatever the problem you select, in this way we can calculate the profit or optimal solution by constructing the tree structure format from root node to leaf node, by considering either element is selected or element is omitted. Okay, na? In LC branch and bound. But in first out branch and bound, we must expand all the nodes in particular level, then only we go to expand next level. But until reaching the answer node, we are supposed to follow that procedure. Okay, na? So in this way, we can solve any problem under LC branch and bound. Okay, so thank you for watching my video.